We are ready to start. Good morning, everybody. My name is Sara Bonella, and I am Deputy Director of SICAM, headquarters here at EPFL. So this is the second lecture in our SICAM Marvel lecture series on classics in molecular and materials modeling. We have the great pleasure of having Professor Michele Parrinello and Roberto Car talking to us about the Car-Parrinello method. I think it's going to be a very interesting morning. A lot of the success of this type of lectures depends on you, in the sense that, and on flies, in the sense that in the tradition of these lectures, we like to keep things as informal and interactive as possible. So in particular, in the second part of the event, which will consist of a conversation between Professor Parrinello and Professor Car and Professor Giulia Galli, in which they will reconstruct for us the history around the creation of the Car-Parrinello method, we will welcome questions from the audience, and let's have fun together. This is part of the point of today's activities. The morning will develop according to, I hope, a smooth and reasonable plan. We will start with a short introduction of the lecture series by SICAM Director, Professor Ignacio Pagona Barraga, that will be followed of an introduction of the Car-Parrinello method given by Professor Michele Ceriotti, who is also a representative of Marvel. Then we will follow with two lectures, the first one delivered by Michele and the second one by Roberto. These will be 50 minutes long overviews and discussions of the method, different aspects of the method. There will be 10 minutes breaks in between the two lectures, and this is an opportunity for you to ask some questions. I would ask you to keep these questions limited to the technical topics of the lectures. There will be plenty of opportunities for you to explore personal curiosities in the second part of the morning. This second part of the morning will be, as I said, a conversation between Giulia, Michele, and Roberto. We have here an appropriate stage. And, well, let's see how things go. Ignacio.
Hello. Hi. Okay. Good morning, everybody. As Sarah just said, this is an initiative that we carry out together between SICAM and Marvel, the National Center of Competence in Research. And the idea of this type of special events came as part of the thoughts and discussions we have had, because this year SICAM celebrates its 50th anniversary. As you know, all beginnings have a certain mythical part to it. The 20th actually coincided with the retirement of the first director, SICAM Moser, who started SICAM. I'm sure that was pure coincidence. But here we are in the 50th, and 50 years is a good time to look to the future, to see what are the challenges. And actually, we will celebrate, beginning of September, a conference to precisely do that. I'm sure most of you are aware, and I hope also will attend to this conference. If you haven't done that, still can approach us to register and participate. And it's also a good moment to look back and see what SICAM has done and has accomplished. And one of the core threats of SICAM has been to promote international scientific cooperation by bringing people together to discuss around in the areas of molecular modeling and computational science, and also in the development and understanding of methods and algorithms that provide scientific insight in how we can use computing machines. So in that sense, we thought it was an opportunity to set up these special events, to learn and reconsider methods that have been particularly relevant and have become milestones in the development of the field. And we do that by inviting the scientists who developed the method, who thought and understood how to sort of move really forward in our understanding and abilities to use algorithms. And as Sarah just said, we do that by combining presentations where the creators of the methods can provide a technical lecture with a presentation of what it is about and what has been the impact of what they started, with the idea that we can record these lectures and create a repository in our server of a set of lectures by the creators of these particularly relevant algorithms. And I think that's something that will be useful for you, but for the whole community. And then having this second part that will allow us to go beyond the standard lectures that we normally attend, and through this conversation to have the possibility to go into the background and the stories of the development and have a more personal touch in how ideas develop and how that happens, which I think it's also a valuable insight. And then having the originators of the methods, I think that's a unique opportunity to do that. So I hope that this will be the case today, that we can, all of us, learn about the Car-Parrinello method by Car and Parrinello, and that you will also, as Sarah said, will learn about the backstories behind it, and you will also have the possibilities to interact with them. So without further delay, I will now pass the word to Michele, who will provide a slight, very broad introduction of the impact that this method has had. And as I said, this also, Sarah said, is also representative of Marble today.
Thank you, Ignacio. So when Sarah and Ignacio asked me to talk about the impact of Car-Parrinello molecular dynamics, I thought, wow, that's tough, because to comment on the impact of something, you must have seen what was before and how this something changed a field or life in general. And when Car-Parrinello came out, I could barely count up to 10. So I think one can say that I have lived all my life with Car-Parrinello method being there, which makes it kind of hard for me to give a personal account of the impact that the Car-Parrinello method has had on this community. So I had to, to rely on kind of a very, very imperfect metric, which is that of bibliometrics and citation counts. But I would like to discuss citation counts, which are kind of a petty metric, but trying to understand what these metrics mean. And if you look at the development of the citations to the Car-Parrinello paper, first thing that you notice is that citation picked up very, very fast. And this is a clear indication of the fact that the Car-Parrinello method was responding to a very pressing need of the community. Very often you get papers that are milestone papers, and there is a kind of incubation time. Car-Parrinello came out just at about the right time because people needed that badly. And then you can see that it has had an exceptionally long life. So it's still being cited at the tune of almost 400 citations a year. And the reason why, in my opinion, and this is not so much based on looking at the citation counts, but reading the paper, the Car-Parrinello paper is much more than a method for performing ab initio molecular dynamics. In my opinion, it's really a blueprint for how you should go about developing a new method for simulations or whatever. There is a clear statement of a problem that needs to be addressed. It picks up ideas from different fields, and it combines them in an elegant and effective way. And it is in this way that you develop something that everyone starts to love and use immediately, and that then can still be used and revered almost 40 years later. And then you can also look at citations in a different way, because what is special about the Car-Parrinello paper is that it was not, a standalone spike that then was used, but it was really something that laid the seed for the growth of a new field and a new community. And you can see this by looking not only at the Car-Parrinello paper, but also at the papers that cite the Car-Parrinello paper and the papers that cite the papers that cite the Car-Parrinello paper. So I did this yesterday evening, and after a while, Google thought that I was basically trying to download their entire citation database, and so they kicked me out. But before they did, so here you can see circles, and the area is proportional to the number of citations. So the Car-Parrinello 1985 PRL itself collected on its own about 12,000 citations, which is in itself very much respectable. But then when you go to and these are just the first 20 top cited papers that cite the Car-Parrinello paper. again, because then Google kicked me out. But just this first layer collected more than 340,000 citations. And if you go, these are, I'm just adding the 5 top cited papers from each of those 20 papers, and we're already at 750,000 citations. So I think that what is special about Car-Parrinello molecular dynamics is really how it generated this network of papers and scientists who have used it and worked on it and developed it further. And I'm really excited to be able to hear from those who were there when it was done, and who were able to count to more than 10 back then, to hear how it was born and how it was used in the early days. So I will not take any more of your time and leave the floor to Sarah, who probably will transfer the floor to Michele.
Yes, exactly. Just a transfer. But thank you very much, Michele, for this enlightening illustration of the importance of the Car-Parrinello method. So I am now going to try to do something very complex. Okay. Very good. So in the tradition of this series of lectures, there will be no formal introduction of the lecturers. I think it's not necessary, and I think it would be extremely long. So in order to keep things short, let's just start with Michele Parrinello.
Okay.
And the Roaring 80s.
Okay. Thank you for coming. When I was invited by Sarah and Nicola to come and give talk, I was very worried that I didn't know exactly what to talk about. Well, for one thing, it's 40 years ago, so my old age, I forget everything. But out of that, I thought it was more useful, also in the spirit of this series of seminars, to describe the intellectual background that led eventually to the Car-Parrinello, some of the consequences of that. That's why the title of my subsection of the talk. So I'll prepare the ground for what then Roberto is going to talk about. Okay, so from my point of view, and for many of others, the moment in which molecular dynamics started in the way that we practice today can be traced back to the work of Anis Rahman, whom I had the great fortune of working with. This is a paper of 1964. It was the first simulation of a realistic system. In this case, it was argon liquid. And there's a structure factor, diffusion coefficients, and immediately in the eye of Anis, there was this idea of making contact with experiment. Okay. Molecular dynamics, as you all know, is based on Newtonian dynamics. So you assume your particle obey Newton's equation of motions, and so if you know the interaction potential in which they interact, the evolution of the system can be followed, and under the hypothesis of ergodicity, you can relate temporal averages to statistical averages. In this particular case, if you do Newton's equation, the ensemble that you sample is one in which the number of particles is kept constant, the volume is kept constant, and the energy is kept constant. There is a small sublet is that the momentum is also kept constant, but that's a small correction of order 1/n. So to all intents and purposes, this is the ensemble which is sampled by. Okay, and so things stay there for a very long time, but one day this gentleman, H.C. Andersen, where, believe it or not, this stands for Hans Christian Andersen. And he's a scientist from Stanford, came up with the idea of extending molecular dynamics in such a way that one could sample more physically relevant relevant ensemble, namely ones in which not the volume, but the pressure is kept constant, and in this particular case, the enthalpy is kept constant. Also, the temperature is kept. This would be the canonical sampling. This paper appeared, I think, in 1980. Was accepted at the end of 1979, and was in print in 1980. It was clear to me immediately that there was more to it than simply technical factor, that you go from one ensemble to the other. Andersen took, in my view, a kind of revolutionary step because he started considering the size, the volume of the simulation box, which, as you know, is always periodically repeated, as dynamical variable, which is added to the position of the coordinate. So, I mean, you know, you start with Newton's equation and you want to touch Newton's equation. That takes a lot of courage. I remember in the early days, people were coming to me after we did the Parrinello Raman that I was going to talk about, and asked me, I will not touch Newton's equation. I stick with Newton's. Okay. So that requires, so we introduced the concept of extended Lagrangian. So the system is supplemented with new degrees of freedom, in this case, the size of the box, and treat thermodynamical variables as dynamical variables that have their own mass and their own dynamics. Okay, that's one thing. So it was 1980. I was visiting Anis Rahman, and we were discussing to do a simulation of some superionic compound. I think it was silver sulfide we wanted to simulate. And of course, the silver sulfide in those days, I mean, getting a potential for things which would be realistically described as silver sulfide was kind of a nightmare. I suggested to Anis, why don't we try to look, because this silver sulfide, I forgot to say, has a phase transformation. It goes monoclinic at low temperature. Why don't we try to get this right? And he pointed out to me that when you do molecular dynamics with fixed periodic boundary conditions, you cannot do it. You cannot do, because in order to go from one crystal structure to the other and be coherent with the periodic boundary conditions, you have to form defects and so on. So that would be impossible. And so the idea came at the time that if we use, rather than cubic, in the spirit of Hans Christian Andersen, rather than using cubic, we allow the cell to vary in shape. This can indeed allow to go from one crystal structure to the other. This is what is called the Bain transformation. See, this is a BCC. If you put together two FCC, you can recognize at the center here, there is a body-centered cell, which is not cubic, but if you compress it, you can go easily from one structure to the other. And so it was natural there to use the ideas of Hans Christian Andersen and supplement now construct a Lagrangian, which I will not write, but which contains as a variable the three axes of the cell, A, B, C. This is the volume, and you allow the things to change, and that's and so indeed it did work. Okay. In the same years, another very interesting paper came out based again on the approach, the Lagrangian approach of Andersen, and it's due to the intelligence and creativity of Sui Shinose, who unfortunately died young, that he was one of the most intelligent and deep person I ever met in my life. Really, it's a great scientist who decided, why don't we try to extend the idea of Andersen so as to control the temperature? And so again, he started writing a Lagrangian, added a new degrees of freedom, ds, which you can think as modulating the scale of time or changing the masses, whatever. You can have many interpretations of this variable. Then his stroke of genius was to add this extra term, and this led in a non-stochastic world to control the temperature. Of course, there are problems and so on, but I will not go into the details. I just want to say this is a child of Andersen paper. Okay, so come with another paper which was important in those days. The other paper, again, it was in 1981, I think. And David Chandler, who sadly passed away not long ago, he visited Argonne, and he made a talk on path integral. So how to treat a quantum particle, and using the famous isomorphism based on the Feynman's quantum statistical mechanics approach. We liked it very much, and so we decided to put to work this formalism in a realistic environment. And but we did it with a twist, using again the idea that was started of adding masses of dynamics, of Newtonian dynamics to degrees of freedom. We treated the beads in the isomorphism as particles. We added the mass to each bead. This is the interaction potential due to the Feynman things, and this is the kinetic energy of the particle. So this was, I think, is what statistical mechanicians nowadays call Hamiltonian sampling. It's probably one of the first times that Hamiltonian sampling was applied, and is commonly used. This approach is at the heart of what is path integral molecular dynamics, which is a way for simulating quantum dynamics. And here there is a little series of pictures which I like to show. The problem we were doing was one electron in a molten salt. This electron, due to Coulomb interaction, is localized. And this shows the Feynman path. At the beginning, the electron is very delocalized. As the simulation proceeds, it becomes more and more crumpled, and eventually it localizes in one spot in the lipid. Okay. In 1984, there was a famous meeting in Argonne, and that was made to celebrate 20 years of the famous paper of Anis Rachman, but actually Anis was already sick at the time, and he had a few more years to live, and that was just the farewell of the community to Anis. And you're wondering whether I am in there? Okay, so indeed. And you can recognize some people that are. This is Hans Andersen, Chandler, Bruce Baird, Charlie Bennett, Dan Frankel is here, and many, many other people. Yakuchi, for those of you who met him, and that's it. That's little me hidden in a corner. Okay. So I mentioned the story of the silver sulfide and getting the potential right, and there was something that was bothering me all the time, and I think many other people. And so we tried to, when I went back from America to Trieste, and then Roberto joined me, we started thinking, what can we do to improve on this side? And can we possibly combine electronic structure calculation with molecular dynamics so as to have a better description of the forces? So, in fact, as you know, the forces that are normally used are really very simple, almost primitive. So it is typically for protein-like thing. So it is a number of so-called bonded interaction, which bond stretching, different bits, bond stretching, bond bending, torsional interaction, and non-bonded. And in many areas, this kind of simple-minded approach has had incredible success. But there are limits. So formation, breakage of covalent bond it cannot be simulated. Only certain kind of interaction are captured. So, and so that, yes, that's the two of us. Some with less white hairs. And so we were coming from different backgrounds, and we decided to combine our abilities together to form a package. And as you will see in the in the lecture of Roberto that will follow mine, we use the Lagrangian. We introduce masses. We attach masses to odd degrees of freedom. So some of the things that have been developed in that paper, they are at the core, at the heart of Car-Parrinello method. So, and why did we do that? In principle, so this was the ideal. No fitting parameters, accuracy and predictive power. So that was the promises of that. Properties that depend on an electron can be calculated on the infrared, Raman, and NMR, electron spin resonance, optical spectrum, and complex chemistry can be simulated. That was the promise. And Roberto will tell you more how it goes about. One thing, So, and I think because of that promises, the community embraced with great enthusiasm what we did. I mean, really, I remember it spread like wildfire. In those days, there was no internet, and you still have reprints, and you send photocopies around, and people, so photocopies from the book, from the bound, from the journal, and we traveled a lot immediately. We had lots of invitation, and we would see in the strangest places photocopies of paper, and young people don't have a recollection of that, but the photocopies there uses some chemical, and that the particular smell of acetate, I don't know, and the lifetime was not very difficult. I don't think they were very healthy. But okay, so that was it. I don't know how much time. Yeah, I can go on. Okay. And we started to apply these things with gusto. Lots of application. We had lots of fun. I remember the first simulation of melting of silicon, which it's an interesting problem because silicon is covalent, but if you melt, it becomes metallic. And how to describe these things was not obvious. We did carbon with Julia. She was a cis young PhD student, and many other sort of simulations that I mean, at least are dear to my heart. We had lots of fun, and there was this feeling of being the first, of being able to do these things. It's a very nice time. Okay, but of course, we bumped also in difficulties, because one is the accuracy of density functional, lots and lots of things of this nature. But one problem that, since I always thought that this method would be extremely important for chemistry, it was the problem of time scale. So ideally, would like to do like in the laboratory. You take reactants, you stir your solution, and out comes the product. Alas, that's not the case on the computer, and because of the famous problem of time scale. And so this problem of time scale is relevant for any branches of molecular dynamics, but I think it's particularly relevant for ab initio, because ab initio, nothing comes for free. So if you want to have all these properties, describe the electron, the breaking, and so on, everything costs money. And so the length scale of computer simulation is very much restricted, and so we worked on that to combine one with the other, and the time scale problem is related to the presence, not all the time, but most of the time, presence of barriers. So if you have a system here, it will fluctuate in the minimum, and if the barrier is high, the probability, the lifetime of this state will be proportional all the area by in an exponential way, and this leads to enormously long reaction time. This is a simple example, and the fact is that in chemistry, like in many other fields of sciences, many physical relevant problems are driven by infrequent fluctuations. Okay. And so we decided to put into place, we tried to put into place a scheme for dealing with this problem, and so and develop a language and a method to approach this problem. And our model is the problem of crystallization, crystallization of liquid, solid. We are at a temperature where the solid is more favorable. What happens here? The liquid has fluctuations, and in which new nuclei of the new phase are formed. This is the number of atoms in this nuclei, and the free energy for these fluctuations will be a negative part, which comes from the fact that it is favorable to form the new phase, and a repulsive term, which is due to the formation of the interface between the two things. So, for small size, this repulsive term will dominate. For larger size, the other, and that's the barrier and the factor of the nucleation. Okay, so this is elementary, but it conveys, hides two messages on how to deal with this complicated system. First message is you don't want to look at a problem from problems of this nature from the point of view of the potential energy surface, which is a very complicated, highly dimensional object, difficult to understand and follow, although there are people like that follow this route. But I come from physics and familiar with the Landau's theory of order parameter and so on. This is the natural way for a physicist to deal with this problem. And the other thing is that, again, like in Landau theory of phase transition, you focus on the free energy as a function of the order parameter. So, in a certain sense, it's like Landau's theory in a sort of microscopic or mesoscopic expression. Okay, so what you have to do in general is to introduce your order parameters, or collective variable, and the free energy associated with that. And as I said, the disadvantages, we go from very complicated, high dimension, to something very smooth, and you can can really focus on the important degrees of freedom also as a tool for understanding what goes on. Okay. Of course, we were not the first to do that, and the mother of all these approaches is a famous paper by Torri and Vallot of many years ago, in which they suggested that the way to sample and determine the free energy is to introduce a potential, which is a function of the collective variable. So you add to the original potential an extra bit, which is able to help you go from one value to the other, and then you can go back from this calculation to the other. Okay, so the issue how you calculate this bias potential, we have developed two methods, an old one, metadynamics, and the newer one, which is, I will briefly talk about metadynamics, which is in a spirit, I consider in the spirit very similar to Anderson thing. And so what you do, so you have a two-well potential. If you don't do anything, your system remains confined in one well. It doesn't go over the other. Then we give a little hand by adding periodically a repulsive potential that fills here and helps our worker to go from one minimum to the other. And that's what it is. Now, when you go, you add to the potential, and that's okay. Okay. the reason why, okay, now you can discuss methods, compare metadynamics with umbrella sampling and so on. One of the reasons why I like metadynamics is the fact that it can be cast in a rigorous statistical mechanics way, and if you do that, you find that the bias that you grow in metadynamics obeys a ordinary differential equation, which I write here. The equation is not important. It is important that it does exist. And the solution of this equation is such that the distribution of the collective variable in the bias ensemble is modified through this relation. So, in other words, the original probability distribution was the red one. So, sharp maximum here, another maximum here, something where the probability is very low, so the system cannot really explore this part and remain stuck either here or there. But when you do metadynamics, you broaden the peak. So you go from the red distribution to the blue distribution. And so you can go from A to B, you can explore the Taylor distribution, look at rare events in anything. So it is this formality, and the fact that it is, why do I say that it's very similar to Anderson? Because you wrap the evolution of your system in a dynamics that eventually leads you to the right statistical mechanics. Very similar to what is done for the constant pressure things. Okay. So if you want to, so that's what we are trying to do. And in other words, the program is going from Switzerland to Devon. So take a big peak and transform it into gentle hills that can be explored. And of course, you have to have a way of going from Devon to Switzerland. I think I will stop here if you don't. I could go on, but I think it's better now that we are in this mode, and that I will pass the floor to Roberto.
As you wish, of course. Thank you very much, Michele. Before passing the floor to Roberto, I was just wondering if there are questions on this first overview that has nicely framed the Car-Parrinello method in the world of molecular
method,
pre, post, and during.
So in all these developments, sometimes the Lagrangian formalism is used, sometimes the Hamiltonian formalism. So I was wondering if it's just a matter of taste, or if there is a particular reason for choosing one or the other.
As far as I know, there is no particular reason. But sometimes the Lagrangian formulation of the equation are simpler than in the other case, more transparent. It is a matter largely of taste. I don't think there is any deeper thing. But you know, Lagrangian is the natural framework when you study classical mechanics. And if you go away from ordinary Cartesian coordinate, you want to treat all degrees of freedom, Lagrangian is typically a simpler way to go about it. But intellectually, no.
Any other question? Okay, if not, thank you, Michele, again. And we can continue this morning's activities with the contribution from Roberto Car. Just thank you. Just 1 second to set things up here. Yes,
with one that works.
indeed. This is on.
Is on?
It is on. Sorry.
Yes, it does work. So I will try to illustrate the ab initio molecular dynamics method, and in particular paying attention on the electronic structure part of it at the beginning, as Michele showed in this drawing of the two guys playing with functionals and with kicking balls on a billiard. But so let me move on, and just to start, let me just show some formulae that wrap up the concept of molecular dynamics. Some of these formulae were already presented by Michele. So essentially, molecular dynamics consists in solving numerically Newton's equation of motion. This equation of motion can be derived from a Lagrangian, and the Lagrangian gives this Lagrangian equation of motion. And I also add one more piece of information here, and that is important also to answer one of the questions that was raised. Why Lagrangian? Well, Lagrangian is directly connected with the action. So the action is a functional of the Lagrangian, and so here we go from time t1 to time t2, and the action corresponding to this Lagrangian is given by this integral of the Lagrangian. And in classical mechanics, there is a famous principle, Hamilton principle, that says that the classical trajectory connecting T1 and T2 is the trajectory that minimizes the action. So this is some concept that I want you to bear in mind. And then, as Michele showed, this equation can be modified in many useful ways, adding thermostat, barostat, and you name it. And the essential issue is that using this molecular dynamics equation, one can sample configuration of the microscopic coordinate psi that characterize the system that have a distribution that is useful to do statistical mechanics. Here I use the canonical distribution, but other distributions are also possible. So we can generate with the straightforward Newton's equation, we have the microcanonical, but in this case we have generate configuration psi that are distributed in a way that is proportional to this Boltzmann weight. Now, all that is very nice and wonderful, but where does the potential energy that we use in this equation come from? So that was the question that Michele and I were asking in Trieste. Can that be derived from first principle? Now, I'm not going in a historical way, but I want just to show that there are that the paper that actually allows us to do that is a famous paper by Born and Oppenheimer that dates from 1927. So we go back to that time, and in that paper they develop an approximation that to deal with the molecular system that is based on the fact that the mass of the electron is much smaller than the mass of the nuclei. And so rather than solving, and they discussed their method in the context of the time-independent Schrödinger equation. That is the one that I gave here, so that is the Hamiltonian. Nuclear kinetic energy, electronic kinetic energy, nuclear repulsion, nuclear electrostatic interaction, and electron-electron interaction. Now, Born and Oppenheimer derived their approximation by a perturbation theory in which the small parameter was the ratio of m over capital M to the power 1/4. But if we are interested in particular in the ground state, as we are interested here, one can derive the same result with a variational approximation that says that the combined nuclear and electronic wave function is the product of a nuclear wave function times an electronic wave function that depends parametrically on the nuclear coordinates. And we solve the time-independent Schrödinger equation for this electronic configuration that for a fixed nuclear structure, because in the first approximation, since the mass of the nuclei is so large, we take it to infinity and they are just fixed at static position. And by solving the electronic eigenvalue problem, we get this energy, electronic energy, and then the nuclear Hamiltonian is very well approximated by this expression. There is an additional non-adiabatic term that I've just neglect here. And so the potential energy for our molecular dynamics simulation is just given by the nuclear electrostatic repulsion energy plus this electronic ground state energy. So this is a great simplification, but computing this electronic ground state energy is still a very hard problem. And in fact, at the time when Born and Oppenheimer wrote their paper, one can do that with enormous approximation and for a molecular dimer perhaps. Hydrogen H2 molecules. So now, so the ground state electronic problem is a very hard problem, and I use here the word of Walter Kohn in his Nobel address. He called the difficulty of that problem the exponential wall of quantum mechanics, and essentially it can be illustrated very simply. Our electronic wave function is a many-body electronic wave function, and apart from the problem of calculating it, even the problem of representing it, storing the data that describe this wave function has an exponential complexity, because if we represent each coordinate on a grid containing m points, the total number of data that we need to store grows exponentially with the number of electrons in the system. On the other hand, if one has non-interacting electron, and in the Hartree approximation, this wave function is just the product of single particle electronic wave function, and then the number of data that we need to store is just linear with n, so the problem becomes much simpler, but the Hartree approximation is not particularly accurate. And so in 1965, so approximately, I think that the Rachman paper was 1964, the Rachman paper on the argon. I think, yes.
Right.
So that Walter Kohn, together with Pierre Hohenberg first, and then with Lou Sham, developed density functional theory. Density functional theory, I write it here, so in the Kohn-Sham form, that is the one that we used. And so in the Kohn-Sham form, one represents, so density functional theory says that this electronic ground state energy is a functional of the electronic density. And this functional of the electronic density, the density can be represented by introducing non-interacting particles, non-interacting orbital, like the orbital that one has here, and then we can minimizing with respect to the density is the same as minimizing with respect to this one particle orbital, and this gives rise to this Euler equation where this Lagrange multiplier serves to enforce orthogonality among this one electron orbital, and this can be written in this way, the Kohn-Sham equation, a Kohn-Sham Hamiltonian acting on this orbital. You see that the Kohn-Sham Hamiltonian depends on the density, is written here, and therefore it requires a self-consistent solution of this equation that can still be done because it is a single particle equation. So again, using Walter Kohn expression, he said to me once, DFT exactified Hartree. And however, it is true because at the end one has this equation that formally has the same structure of the Hartree equation, but it is exact, at least formally. It would be exact in practice if we knew the form of this exchange correlation potential, which is a local potential in R, but it is a very complicated functional of the density. So both the exchange correlation energy that enter in the definition of the Kohn-Sham energy and the potential, which is just the functional derivative of that, need approximation. And the approximation that was very popular in the day that Michele and I started to work at the Car-Parrinello was the local density approximation. The world was much simpler in those days, and the local density approximation was brought to the attention of people doing calculation of material by the work by Marvin Cohen and collaborators at UC Berkeley. They showed in the beginning of the 1980s that DFT with LDA could predict stable crystalline structure and pressure-induced structural transformation of silicon and germanium. And that was a matter of great excitement because since the time of Wigner in the 30s, people wonder, can quantum mechanics predict stable crystalline structures? And the answer was yes, quantum mechanics could predict stable crystalline structure, in particular also of systems that were thought to be very complicated, like semiconductors, silicon and germanium. And at the time that we were starting to do our work, well, I came back also from the US, to Trieste, from the IBM research laboratory in Yorktown Heights, and at those times people were starting to see, well, we can predict crystalline structure. What about adding some disorder to this crystalline structure? The disorder was just one vacancy or one impurity atom. Can we predict the formation energies of, for instance, a vacancy or a self-interstitial? And so at that point, and all these calculations were done at zero temperature. So it was just dominated by the energy at zero temperature, no free energy, just pure energy at zero temperature. Now, as I said, in this Kohn-Sham formulation, one has a set of fictitious non-interaction electrons, so I will use compact notation. This electronic state made by non-interacting electron is given by a determinant of this Kohn-Sham orbital, and the state that minimizes the Kohn-Sham energy for configuration, for nuclear configuration R, is given by this particular determinant. Now the question is, if we want to use Kohn-Sham energy to drive molecular dynamics, we need to compute this thing efficiently and fast in order to be able to do that for many steps during a molecular dynamics trajectory. And so how can we do without solving the self-consistent Kohn-Sham equation at each step? And here is where the Car-Parrinello Lagrangian comes in. In this Lagrangian, there is a fictitious, we consider the nuclei and the electron as independent variable. From this Lagrangian, where mu is a parameter that characterizes the dynamics of the fictitious electrons, this is a Lagrange multiplier that imposes the normalization here. From this Lagrangian, we can write down this equation, and the evolution in this equation will be adiabatic, namely the electron will adjust to the instantaneous state of the ion if the electronic dynamics is much faster than the nuclear dynamics. And the electronic dynamics, the frequency, the minimum frequency of the electronic dynamics is to very good approximation given by this simple expression, the square root of the energy of the gap in the system divided by this mass parameter here. If we start in this equation with the Kohn-Sham ground state at t equals 0, then the system will evolve with the electron always wandering around the instantaneous ground state if these conditions are satisfied. How to get the Kohn-Sham ground state at t equals 0? Well, we can do in many ways. One way that we can simply derive from that is to use damped Car-Parrinello dynamics, in which we add a friction term acting on the electronic degrees of freedom. And so in this way, we can obtain the ground state for a given nuclear configuration and then start this thing. However, as I said here, there is a problem when the electronic frequency does not satisfy, the minimum electronic frequency does not satisfy this equation. And in addition, if the mass parameter, if the dynamics of the electron is not sufficiently fast, well, we recover, of course, the true adiabatic dynamics in the limit mu going to 0, but in simulation we have to use a finite mu, so there are difficulties with metal, and if mu is not sufficiently small, there is an electron drag on the dynamics of the nuclei that modifies a little perturbed the correct Born-Oppenheimer dynamics of the nuclei. So this led to the dichotomy CP versus BO, but there is no real dichotomy because it can be simply solved by hybrid approach, in which one combines a CP step with several steps of damped dynamics to keep the system always sufficiently close to the electronic ground state. This is just to show some early applications. So this was the liquid silicon that we were mentioning about. This is taken from this paper by Ivan Stich, myself and Michele. Ivan was one of the first students we had in Trieste, and I mean, this is, you see here, this is a crystalline. This was very popular in those days, coming from the work of Marvin Cohen. The electronic, the valence electronic density in silicon that was calculated with this density functional calculation that showed the, well, these are atoms, and there is here a covalent bond, a bump in the electronic density in the region between the two atoms. So what happens if the system becomes disordered? As Michele said, the liquid silicon is metallic, but covalent fluctuation remain also in the liquid, and there are some configurations that in which one can see a configuration similar to this one, but if we let the system evolve over a short time, some fraction of a picosecond, the covalent bond disappear. And this covalent fluctuation explain the structure of liquid silicon that is different from simple liquid metals. Well, I would like to just mention one thing compared to the thing that one can do nowadays. I think that this simulation we were able to explore a time scale of maybe 2 picoseconds or 3, I don't remember, and then, but was on the picosecond time scale. Well, molecular dynamics opened the door for statistical mechanics and computing thermodynamic properties. This is a work that we did with Osamu Sugino, who was a postdoc when I was here in Lausanne in the 90s, coming from Japan. And you can see melting temperature based on LDA, and a number, entropy of the crystal, entropy of the liquid, and various thermodynamic properties. Well, the agreement is not bad, I would say, and this was based on the LDA. And, well, melting temperature is off by a few hundred degrees, but overall, the agreement is much better than what one can do for all these properties one could do at the time with empirical potential for that system. So this is, was an important step forward. Now I want, well, how much time? Okay. Well, in all that, we have used classical mechanics to describe the nuclei, but classical mechanics may not be enough for a number of studies. Can we deal with the nuclear motion quantum mechanically? Well, as Michele already mentioned, the which one is that? No, this one. As Michele already mentioned, a way to do that is provided by Feynman formulation of quantum mechanics. Now, the reason for that is that in the classical world that I've described so far, the position of the nuclei, these are C numbers. So they are classical variables. They commute, and they are very easy to deal with. But in quantum mechanics, if we want to describe these nuclear coordinates, they are operators, and they are operators that do not commute if taken at different time, because they do not commute with the Hamiltonian. That is what allows us to propagate them in time. So we would like to have C numbers in order to do to be able to compute properties with the machinery that I've described. And Feynman, in these famous papers of paper of 1948, just showed that one can represent the time propagator in quantum mechanics as an integral over the path, where each path, so in classical mechanics, if I want to go from A to B, there is just one unique path that the system will follow, and this is the path that minimizes the action. Instead, in quantum mechanics, we have an infinity of paths, and each one of these paths has a weight that is given by this exponential of the action. And the action, I said before, was a functional of the Lagrangian, but I can see also as a functional of the path. So that is the representation of the time propagator in quantum mechanics. Now, a difficulty with that is that this object is complex, and so the classical molecular dynamics or statistic Monte Carlo method are not good to sample the distribution of this path. But if we go from quantum dynamics to statistical mechanics, what we have to do, we have to replace this object here with this Boltzmann weight, and this is done by doing what is called a Wick rotation, namely we go from real time to imaginary time tau. If the imaginary time tau is equal to beta h bar, you just substitute for t, imaginary time t, inside this action, and what one get, well, if we do that in this thing, we get this object, and if we do it inside the action, what we get still an integral over the path, but the action is replaced by what is called the Euclidean action, and this Euclidean action is the integral of a Euclidean Lagrangian, and the Euclidean Lagrangian is just the sum of kinetic plus potential energy. So when we have something like that, then we have something that is equivalent to a Boltzmann weight here, and therefore we can use the molecular dynamics machinery to sample the path rather than sampling the position of point particles. And that can be done, and can be done also in the context of ab initio molecular dynamics. I want just to show you one example. Well, in order to sample the path numerically, the paths have an infinity of points, but in order to sample them numerically, we have to discretize, and the discretized paths give rise to these objects that are called ring polymers sometimes, or necklaces. Michele was calling them necklaces in the old days. Depending on the property one want to calculate, one might need also open polymers like that. So essentially the quantum particle is replaced by a set of beads that are connected by springs that have a particular force constant that can be derived from the Feynman path integral formulation. And just to want to show you one example here, this work we did, Joe Moron in Princeton, and of course these quantum effects are going to be more important if we have like nuclei, like the protons, and this here, this plot shows the momentum distribution of the momentum of the protons as obtained from experiment. These are these points in a system made by water molecule, either liquid water or ice, and these continuous line are the result of the simulation. This dotted line that will continue up here is the Maxwell-Boltzmann distribution that one will have in classical mechanics. So you see that the distribution is quite different from the Maxwell-Boltzmann distribution, and in addition there is a difference in the tail of the distribution between water and ice. So the momentum distribution becomes sensitive to the local environment of the proton, whereas the Maxwell-Boltzmann distribution just depends on temperature and doesn't care of the local environment. So one can see this kind of thing, and with the ab initio path integral molecular dynamics, one can actually predict this property and find decent agreement with experiment. Now I want just to go to the very last. Of course, I've not discussed many areas. I've only showed some example in systems that are quite simple, particularly in the world of chemistry. There are systems that are extremely complex, complex molecules, biological molecule, and also for this system, these approaches have been used successfully. As Michele mentioned in his talk, one difficulty that one has with this simulation is the time scale of the simulation. At the time of we were in Trieste, we could sample a trajectory for a few picoseconds. Nowadays, people can sample trajectory for hundreds of picoseconds, but if they have a powerful computer, but that is definitely not enough. We would like to go to much longer time scale, similar to the time scale that one can reach with empirical force field, and also one would like to deal with much bigger systems. So there is also the size problem, and of course, even if one does that, one will not solve the problem of rare events, but the problem of rare events requires enhanced sampling technique like metadynamics, for instance, but these techniques require a sampling that is quite extensive and cannot be done for complex system in condensed phase by doing, other than in some special cases, by doing straightforward ab initio MD. So an area that in which I'm very interested nowadays is boosting ab initio molecular dynamics with machine learning, and we have developed a technique based on deep neural network that we call deep potential molecular dynamics, and essentially this is a picture that one student in the group prepared to illustrate this concept. So this is a water system. This is the water box that we can do with ab initio MD, and this is the number of frames, time scale, but when we use this deep neural network, we can go to much bigger system and follow the evolution over a much longer time scale. The power of this deep neural network is that they can represent the potential energy, ab initio potential energy surface with extreme accuracy. And they have essentially the potential energy surface is represented in this way as a sum of local potential, where each one of these local energy function is actually a many-body potential that depend on the environment of the atoms. With this expression, one can represent, and we use a simple convolutional neural network. With this thing, one can represent any potential energy surface with large accuracy, and one can see that one achieved a dream that we have in the early days of the development. Julia, for instance, was very much involved in developing what are called order n method to do ab initio molecular dynamics. Now with the neural network and with this representation of the potential energy surface, we have linear scaling, whereas the standard ab initio MD calculation have asymptotically cubic scaling, and these are the result with two different energy functional. The more accurate is this one. So you see we gain many orders of magnitude compared to the standard ab initio MD, and we get close to what we would do for this system. In this case, it was water, using an empirical force field. I want to say just a couple of words here that in representing this potential energy surface, we have to satisfy symmetry properties of the system: rotational, translational symmetry, and permutational symmetry. And this is done in our approach by using descriptors that do not include any artificial construct, just using the coordinates. The descriptors are just based on the coordinate of the atom. There is no parameter that have to be fitted or adjusted, and it works quite nicely. Now, just example of two applications still with small system, but we are doing, well, this is still small, but still is, this is 500 molecule with at the level of hybrid functional, and we do with DPMD, we can do the PI DPMD for heavy water and for light water, and you see these small differences that one see in the pair correlation function actually compare quite well with what is observed in experiment. And one other application that I want to mention here is an infrared absorption spectra, again of light and heavy water at the level of a hybrid functional with 500 molecule, and this to get very good statistics. Here we did for time of the order of a nanosecond, but we can do more than that. We can do hundreds of nanoseconds, and we have simulation with tens of thousands of molecules. This is possible. And this shows the agreement that one gets. One has to compute this correlation function, and this correlation function is calculated in this case using classical mechanics, whereas here these static properties are based on the path integral. So where do these discrepancies with experiment come from? Well, one obvious thing is that we use here classical mechanics rather than quantum mechanics, and the other thing is that we rely on density functional theory with a given functional. We do not know what is the accuracy of that to describe this system, but is not bad. So with that, I think I can come to the conclusion, and just mentioning some open issues and issues that may be at the basis of future work. Some of these involve very difficult problems, and maybe one of you will be able to solve this problem in the future. So there is some reason for not being satisfied with the FT, with the present state of the FT. When we started at the very beginning, there was this LDA. LDA is well defined. There is a unique LDA just based on the homogeneous electron gas. There are no other parameters to control. One does the best calculation that one can do for the homogeneous electron gas, and that was done by quantum Monte Carlo calculation by David Sepperly and Bernie Older, and one just fitted the exchange correlation energy density obtained from these quantum Monte Carlo calculations that are very accurate, and one uses that in the calculation in the solid. But that is not good enough for many systems. For silicon, it works well, but for instance, for water, it would be a disaster, and for many other complex chemical systems using LDA would be a disaster. So there has been a lot of progress at the time when I was at the time in the Trieste days. I was thinking that LDA was the end of the story with DFT, and in fact is not. But the thing that is not satisfactory is that there is a plethora of DFT functionals, and is not easy, even though there has been improvement in the description of materials and molecules. The improvement is not systematic. So can we achieve systematic improvement? There are some roads that one may follow, move further up on Jacob's ladder within DFT, so going to higher order DFT approximation. But I'm not sure, again, I'm a little skeptical about all this DFT. Maybe it's going to work, but at some point, if one goes to higher level in the ladder, the calculation become very expensive, and they become as expensive as good quantum chemistry calculation. So perhaps one could get input from wave function methods rather than density functional approaches, namely quantum chemistry, quantum Monte Carlo. And in this area, I think that machine learning can help moving forward, because we may not need to get this accurate result for a very large number of configuration if we use machine learning and some incremental learning techniques. The other area that I want to mention is quantum dynamics. I already show a result of the infrared spectrum. This is based on linear response theory. So let's stay within linear response theory. Can we compute the dynamic response function using the path integral formalism? Yes, we could compute using the path integral formalism, but then we can compute them in imaginary time. We have to go back to real time, and that involves an analytic continuation. Analytic continuation is made extremely difficult by the statistical noise of the simulation, but again, the machine learning can help to reduce the statistical noise, so perhaps something is possible. We can get much more accurate because we can run very long trajectories, have small statistical noise, and perhaps we could follow this thing. Other ways is to explore approximate methods for time-dependent correlation, like semi-classical, or method based on short time expansion. Finally, there is the issue of coupled dynamics of electron and nuclei. Beyond the Born-Oppenheimer approximation, there is a lot of work that has been going on this issue, and that I think is also a very important problem to be able to do that for system in condensed phase. Most of the progress has been done in molecular system, but to be able to do that in condensed phase is one of the big challenges in which some important conceptual advance is needed. And with that, I thank you for your attention. Thank you.
Thank you, Roberto. So we are now ready for questions on this lecture. There's one in the back.
Yes.
I have a question that is half historical and half about the method. So the first applications in the first paper, and then the ones on silicon
Yes.
I wonder whether you compare the performance or the boost that you got with the Car-Parrinello with a Born-Oppenheimer, pure Born-Oppenheimer, and which kind of properties you had access to thanks to the very algorithm of the Car-Parrinello, or the very idea of the additional terms in the Lagrangian and the mass.
Well, simple answer is that at that time, to do a simple-minded full Born-Oppenheimer would not have been possible. We tried that because we experienced a lot of things on a small system, but we were doing, for instance, enforcing the Born-Oppenheimer criterion by doing essentially steepest descent. By doing steepest descent, there are orders of magnitude. So we were able to explore, I don't know, 2-3 picoseconds. Maybe we could have done a few femtoseconds. So that was the issue there. We also tried because. Well, we were helped. Silicon is metallic, so in the metallic, we did the straightforward CP without thermostat or without damping and things like that. That can be done later, but we were helped by the fact that we were doing short trajectories. On a short trajectory, even though there is some mixing in a metallic system between the nuclear and the electronic motion, that most of the electronic occupied state do not mix because they are below the Fermi energy and they have a gap. And so there is some mixing for the state at the Fermi energy, but the state at the Fermi energy has similar character for the occupied and the unoccupied state. So even if you mix them a little bit, the result for the structural properties remain the same. So we were lucky with that. If we did other system more difficult than silicon, we would have faced difficulties. But of course, also regarding to the Born-Oppenheimer and the way to enforce Born-Oppenheimer, one important concept that is in the Car-Parrinello method is that you do a dynamics, and so you extrapolate the new wave function by knowing the wave function and its velocity, if you want, at the previous time step. And so all methods, people doing electronic self-consistent calculation were not used to that. And so one had to include that in the electronic self-consistent calculation, a way to get a good extrapolation of the new electronic wave function, and then maybe optimize that to enforce Born-Oppenheimer condition, and that is also what was brought by our approach, I think. Yeah.
Other questions? Okay, I think we're all impatient to move to the next part of the day. So thank you again, Roberto.
Thank you.
And so it is now my pleasure to ask Michele to come back here on stage and to ask Giulia Galli to also join us to help us move along. You just keep it.
I
Yes,
keep it.
absolutely.
But then...
Okay.
No, I cannot sit in the middle of the...
No.
No.
You
No.
Okay,
You have to.
I sit in the middle between the two of them, okay.
Just be careful there.
Yeah. I'll be very careful.
be careful not to fall down.
Oh, come on.
All right.
Okay, the stage is yours. Thank you very
Okay.
much.
So the microphone works, right? Okay, good morning, everybody. And I think the idea is that we start a discussion with the two speakers, and I will be the first one to start the discussion. My name is Giulia Galli. I'm from the University of Chicago and are the National Lab. And I guess the reason why I'm here this morning is because I was a PhD student in Trieste when all this happened. And I interviewed in Trieste in 1982, and of course you can do the math and see how old I am. Don't. And Michele was in the committee of admission in CISA, and I arrived in Trieste in 1983, and in 1984 Roberto arrived, and I told this to many of you already. And when Roberto arrived from IBM, we were asked, myself, the late Sandro Massida, and Annalisa Fasolino, we were asked to move away from my office, to leave room for Roberto, who arrived from the United States. And we formally complained to Elio Tosatti, who was the head of the CISA sector of condensed matter at the time, saying, we don't want to move, and by the way, who is Roberto Carr? You know, and Tosatti looked at us and said, okay, you move, you shut up. I don't know, if for those of you who know Elio Tosatti, this will not come as a surprise, and so we moved. And then Roberto took our office, and but he didn't stay there very long, because then he joined Michele in the office when Elio went on sabbatical. I don't remember where Elio went, actually. But anyway.
He went to Zurich.
Oh, he went to Zurich. Okay.
Yes.
So anyway, this is the beginning of the story, and so of course the first question is just to then give the floor to them to tell us how it all started. And I think the question that I always have, and I always ask myself also when I, trying to motivate my student, is what is that really make possible new development? What is that support the creativity of people? Why this happens, and could this have ever happen today in a environment where we are much more constrained by grants and centers and stuff like that? I don't know if you want to talk to that.
Okay, there are various, it's a complex questions. A complex question. I tried to indicate in my talk that it didn't happen by chance. There was something going on in the literature that led eventually to do the big step and go all the way to the Car-Parrinello. So that's the other important thing for this to have happened was the incredible climate and atmosphere scientific at CISA in Trieste in those days. There were a number of talent there, like Baroni, Annabella, Elio, many other people, Resta, and total freedom that we had. We could do whatever we wanted, as long as it was good stuff. Nobody would tell us, do this, do that, do the other. And this point, I also to say, to thank the generosity, for instance, of Baroni, that on the technical side, it has helped us in many ways.
Yes.
And the other thing I will say also, the solidarity. When we got the first CP running, the whole group, without any envy, without anything, went to celebrate it. So we went, there was a bar there, we went, and so on. We drank together to this success. So that was, Trieste is still a special place, but I think it was especially special in those days. And there is also an important fact. I mean, that's we were much younger, Roberto and me, and we were also brave, or sort of, there was, I think there was nothing that would have stopped us. We had the feeling we could conquer the world.
Yes.
Which was quite, it's been unique in my life. So all these things are made possible. There's a background. There was also a need for that. As Michele Ceriotti was saying, the community responded immediately. It was just incredible, wildfire. And this was compounded by the fact that I've been told, that I've been committees that I discussed the possibility of doing combination of DFT and molecular dynamics, and the conclusion was that it would have been possible in 10, 20 years. Instead, they saw that, by doing things different, it could have been done much earlier. And in fact, we got first non-trivial result, and it was a great time. How should I say? So there was a special place and a special time. Now things are more difficult. But even there, as I say, Trieste was an exception. Even there, then, for instance, I know because when I left Trieste, I went to IBM, Zurich, and when they got 2 Nobel Prizes. And the work they did was hidden from the manager before they got the result. Otherwise, they couldn't have done it. So there is something.
Yeah. No, perhaps just to add a few things. Certainly, we didn't have to write any grant proposal for what we did. That
would have been rejected on the basis of the committee report.
It would have been rejected immediately. And
they would have called the ambulance.
One other thing that a couple of recollection. One that, I mentioned Walter Kohn a few times in my talk. Walter was a great scientist and a great man. And one of the things that he told me once was that when you have a situation like the one that we had in Trieste with not a very, there was no space for the people. People were just arranged in very ad hoc ways and things like that. Is the situation where people get together more closely because they are forced to, and they interact more, and there is more productivity. So he mentioned that something like that happened in the group of Piles when they had that he visited, and he said that in Piles' group at the beginning were something like that, like in Trieste was a mess, but there was great productivity. Then finally the success led to have a very nice building, everyone with his own perfect office and things like that. And the productivity actually went down. So that was one of the things that Walter mentioned to me. And another thing that's still a recollection of the time in Trieste about when I was there, I was a nobody, and but with this thing, there has been immediately great success. And I don't remember when Ken Wilson came, that ICTP was hosting a lot of conferences with very famous people in summer. And in one of these things, Ken Wilson came. I think it was 88, perhaps,
yes,
or something like that. Ken Wilson came, and he had, at that time, there were no laptop computers, and you have the. Okay.
Let's see whether, continue. Let's see whether I find it. That's the issue.
I must have it also, but let's see. That's right. That would be. So let me tell the story. people were just drawing on a plastic piece, transparent piece of paper, and there were this projector. And Ken Wilson mentioned that about methods that are very important, and that this was 88. I was not expecting something like that from Ken Wilson, that method like the Car-Parrinello method will stay for decades to come, or something like that.
Yeah.
And we were immediately, since at the ICTP situation, at that time Abdus Salam was still alive, and the culture was high energy and field theory culture. So people doing condensed matter physics like us were always considered second class, sort of second class citizen. And after Ken mentioned our work, all our high energy colleagues were just coming to congratulate us. Wow, you have done something, something quite important.
I don't find it.
Well, we have a copy of the slide that
Oh, I see. That's
that Ken Wilson presented in those days. Yes.
So before I go on with the other questions, are there any questions from the audience? Historical, not historical, anything? Yes, Federico.
Just for a sec, please. Wait for the microphone. Thank you.
Okay. No. I have one that is mainly a curiosity. Okay, but was there anyone that fought you and like told you that you were wrong? Okay, clearly you were not, but were there anyone that says no, this is impossible, it doesn't work, and so on and so forth? To your memory.
No, well,
yes.
well, they after the fact they told you they can do better, and that we were.
No, that's right. Well, there were the electronic structure people who said, well, that is impossible, but then they saw the result, and apparently also, again, that was something that Bob Jones told me once, that he was at Cornell, and they discuss our approach. Some of the big people discuss our approach and consider that to be quite a new important development, and so that immediately helped getting.
No, the beginning was all roses.
Yeah. Sure.
The thorns came later.
Yes.
Anybody else? So I can tell you one other of my recollections that will lead me to my next question is that when we were working in Trieste, we had some terminals in one very, very small room, and we were always fighting for the access to the terminals and to the computers. And these were the first days when we could actually run simulation. When we started, I was one of them, and also other people. I was at the end of my PhD at the time, doing Car-Parrinello simulation. So the question that I have is related to which role the fact that you didn't only invent the method, but you very quickly implemented it and ran it on the big machine of the time had. I mean, it was a
big machine.
Well, but if they were the big machine, I mean, if you think about this, this is a combination and actually an explosion of accomplishment, right? So there is an idea that is implemented, and there is an idea that it's implemented, well, apart from the Gould, the computer, but also it's implemented on the Cray, which was the largest machine at the time, and that allowed you to run liquid silicon and so on and so forth. And by the way, the first Car-Parrinello code had a title which was Molecular Dynamics for Silicon, which stayed there forever. And we were all printing out, also myself, I was doing Molecular Dynamics for Silicon, because we didn't even bother changing that. But anyway, so what is the role that, in your opinion, being able to implement and to have a code running on this bigger machine had on the success?
Okay, Car-Parrinello has many components to it. Also in the way the electronic structure calculation are carried out. And Roberto had already thought about these things, and he partly implemented, not all the way, but
Yes.
partly implemented. So that helped a lot. And then we did work like crazy.
Yes. Every night.
Every night.
But
We would go back home. Maybe I can tell the story.
Yeah.
Go back home for dinner. Then we went, he came, typically he was driving, always parasiting is driving. We would come home, pick me up. We would go to a sort of trendy bar along the costiera
Yes.
to have a coffee. And
At 9
this
in the
bar
evening.
was full of this pretty Triestino girl and so on, all elegantly
Drinking
dressed.
beer,
And these two miserable nerds who looked like that. Anyhow. and so we went there and we stayed until very, very late.
Yes.
There was a porter that would have to
Enter the-
open the building for us. He never complained, poor
Yes.
man. In the night, we drag him out of his warm house and would from self-restore.
But what was the role of
Of
being
what?
able to use these computers, or in
Oh,
general?
no. I mean,
And in general, after that, the role
no. We're talking about serious things. The fact that there was a component of luck, because Cineca in Bologna, the computer center, bought the first Cray for ITER. And without that thing, I mean, things would not have been so fast.
That's
I think
right.
there was like in many things in life, there is a strong component. And there was a problem with connection.
Yes.
Oh, yes.
Yeah. So the line was very poor, and we needed a fast line, and they were very creative for doing that, because buying the line would have been too costly. So they they got money from some satellite transmission experiment, and so they implanted in the garden of Sisa a big parabola that would transmit the Car-Parrinello code up to the satellite and
then to
down to
Bologna.
Bologna.
Yeah. Both.
Both. We were
Both.
sitting there together. In
Yeah,
fact, there
yeah.
was a terrible code.
If you show the code to a
I mean,
computer specialist, he would just say, rubbish.
The working code for the machine, was there anybody else that helped?
No.
It's all our responsibility.
No, I must say that the first, because at the beginning we had this Gould computer that was a poor computer, but in the first, in the paper that in the PhysRev letter that we published, we use a very simple system, silicon, and even local pseudo-potential, because that was
all we could afford.
But then we went in summer. We went to IBM, and at IBM we worked to implement a non-local pseudo-potential in the code. And but at the IBM, even the IBM had a new computer at the time, but it was difficult to get, particular for two visitors. But eventually they gave us the possibility to run on that computer, but was much worse than the Cray. The Cray was really
because it was a vectorial machine.
I mean, the IBM was better than the computer we had in Trieste by any means, but not as good as the Cray. And when we came back, there was the Cray in Trieste, and that was in Bologna, and that was what made possible the calculation of liquid silicon that and amorphous silicon that we did.
I have a question related to the, let's say, future and how you see the machine learning thing coming up. Let's say at some point the machine managed to beat the human, Garry Kasparov, and that was a major breakthrough. In 2012, there was a major breakthrough in image recognition, such a point that NVIDIA changed a line and invested heavily into this technology. Do you expect any major scientific breakthrough, and if so, when that you could see happening in science and in condensed matter?
Well, as the guy says, you can make prediction safely only on the past.
Yes.
But I think it's safe to say that machine learning will play an ever greater role in what we do. In my mind, there is no question about that. Yeah. It will become one of the main tools of our trade. And for us, it's important that we never lose touch from the physics. And not only because that's our job, but in the end you have to come up with a model, humanly understandable model. But also because if you adapt the machine learning algorithm to the physical problem, then it becomes much more powerful. So it's something that goes two ways. Huh?
Yeah.
I think it goes two ways. I don't know.
Yeah, I agree. And I mean, it's a very powerful technique. We have used it in some context, and it allows to boost the power of the simulation that we are doing. But having access to this very powerful tool, I think some people using that tool could come up with some new concept. I think that is where, when you make a real breakthrough, and being in the physical science, I think that the new concept must be some new concept in the physics. For instance, the fact that you can model a system in that particular way, and that is only possible because there is that particular technique that is now available, and it was not 30 years ago or things like that. So that, I think, is definitely, I think is going to happen, and it already happens in many.
I personally am investing a big fraction of my time in machine learning. So that's an answer to what I think about machine learning.
Yeah. Any other questions? Well, I think that one question which is kind of obvious to ask to Michele and Roberto is what kind of suggestion they have for people, right, who are moving in the field. And having known them for more than 30 years, one thing that I've always experienced with them is the kind of enthusiasm that they can transmit to you. And you talk to them at any stage of their career, and they always have something to tell you, and sometimes in a very disordered way. But it's always with an incredible enthusiasm. And this has been going on for more than 30 years, and I don't know many people like that, I must say, although I've talked to many people over the years. So how do you keep the enthusiasm going, and what do you want to say to young people to keep the enthusiasm going or growing?
Well, Okay, so you have to remain a child.
Yeah.
You have to remain a child, and I think in some sense we have been lucky, both Roberta and me,
Yes.
having been able to remain children. And we derive great delight, I think, in what we do. And I think this passes on to what.
Yeah.
So I don't like just to give a problem to the postdoc or student and then wait for what they do. They come up after months and months. I like to be involved every day with what happens, with the progress, and so and rejoice with them when there is a progress, and trying to help them when there is a difficulty. So that's I suppose why. Why do we?
No, I'll let Roberto respond, but I have another question. Please.
Yeah, no, I think that the fact that we could do what we like, we are very lucky.
Very lucky.
And I mean, and science is a search for better understanding of some phenomena in the world, and you get very excited when you make a small step forward, and that is what is the major reason of satisfaction. Another very important thing is the fact of being in contact with young people who have good ideas, and the young people always have good ideas. So it's being able to help young people and to refine their ideas or apply to some other thing, because with experience now we know that one can do that and connect that, but that is also a major source of excitement, and
that is true, and in fact, I mean, all the progress that have been done in Roberto's group, in my group, and so on, would not have been possible without the collective intelligence of the group and the generations of talented people that have worked with us. That's absolutely to be underlined.
So, last suggestion to all the young people in the audience, be brave, maybe.
Sure. I would say, ignorance helps.
Yes.
In the sense that if you know too much about the subject, you also know all the prejudices and of the community. So if you, within limits, if you don't know too much, you have less barriers.
Yes, no, that was very important. In fact,
less mental barriers, and it's easier for you to go. Because then, no, this is, I cannot do.
So exploring other fields.
Yeah,
so
that's right.
I think
you have an idea about something. You don't worry, but will it work? Will it not? Try, and then if there is something good, it will develop, and you will understand more. And in fact, prejudice about the fact that that was not possible. We could do it, but then we understood better that there were some pitfalls that we completely overlooked and that were important. But then that leads to deeper understanding and to new ideas, because you realize that there are some other problems that you have to solve.
Any other questions or comments before we close? Ignazio.
It's a historical curiosity because Michele, you have said that the beginning was rosy and then it became harder later on. So
No,
I don't know in which sense or what was
not really hard, but people began to criticize. I could be done better. I could do this. Oppenheimer,
exactly.
All those things. But I would say that's basically it's been all rosy.
Yes.
We've been lucky.
Yes.
Been lucky. That's sort of the minimum that could have happened to any.
Anything else? Some crazy question? Franz?
My question is about the computing environment that you had available at the time. So at the time, vector computers were coming up online, and you had to do extra work to adapt to that and then take advantage of this. Yeah. So now translating to what happens today, and things are changing fast too, and contrary to what happened at the time, vector computers were intended to support scientific computing. What we see today is not made at all for scientific computing. So how do you see the future there? Should we just start thinking about mapping all our physics problems into image recognition problems so that we could eventually take advantage of things? Or can we as a scientific community still have enough weight so that computers could still support scientific computing?
I don't know. It's a difficult question, and I think facts are speaking for themselves. So, no, we don't have enough power to, and I think we have to get along with that. Maybe if we were in the quantum computing kind of close to that, there would be possibilities. I don't see that the commercial drive is so strong that they will not. And developing science, dedicated machine, it's an expensive do.
Yeah,
maybe Europe could do it, but no commercial thing.
No, I think that also in the past, essentially, it has been driven by the market forces, what computer we could access.
It's right. Clay was aware of our need and built a machine which was great. I mean, we had to do matrix multiplication and fast Fourier transform on the machine. They went like that.
Yeah, but the alternative of trying to build a dedicated computer, several people did, but in the end, I don't think that it was very successful. That is my...
Well, there's been one exception. The D show invested 60 million and built a machine. I think which, I mean, can do only one thing in a special way, but it has provided us with important data. The drive is again commercial. It's from the drug industry. That's what it does. So, but even the show, I understand, is now doing enhanced sampling. So that simply implies that we are really getting to the end of the thing. And as Alessandro was saying the first day, we are possibly at the end of Moore's law. So, so it's life. There is nothing wrong with thinking, translating our problem into image recognition.
Machine learning. Machine learning in a way. Yeah. That's all right. Well, yes, please.
So in the end, your encounter has been quite powerful and fast because since Roberto arrived in Trieste until 1985, the publication of PRL, there was not much time. So this means that the two of you meeting together, lots of ideas came, and maybe all the environment in Trieste was very beneficial. But typically, I mean, when people interact in the ideas are intertwined and entangled, but typically there is some input from someone that helps a lot the thing going on. So my question is to Michele, what was the input from Roberto that in your opinion was fundamental, and vice versa, or Roberto was the input from Michele that helped Roberto Car-Parrinello?
You want me to say something? Well, certainly the very, I did not know about molecular dynamics when I met with Michele, and I remember still something that I was thinking in terms of optimizing crystal structure and using the forces to optimize crystal structure. And Michele told me, but one can use the forces to do something better than that. And that was a big revelation. And so that definitely was very important.
Yeah, no, certainly there were complementary expertise, and there was not only, but both of us, we were able to talk to one another.
Yeah.
That's also important thing, because different people, and I can have an education in solid state and so on, so he was familiar with the language and the problematic of things, even if I was not at all deep and not as much as Roberto. Then it's a question of also personality. I think like in a marriage. It has lasted 40 years.
Yes.
All right. So shall we thank Michele and Roberto for the lecture and review session? And I guess there is a reception.
So I would like to thank Michele and Roberto, but I would also like to thank very much Julia for animating this session in such a lovely and interesting way. Michele Ceriotti for getting us started. And then SECAM and Marvel to enabling all this, just because, right? Okay, so this is our second lecture of this series. There will be more in the fall. Please stay tuned on Marvel and SECAM websites. Also, we will eventually upload all these lectures on our archive, and you will receive news of this via email and Twitter. Thank you very much for coming.